most experiments, you can plan what you want to do. In astronomy, you have to wait for the light to come to you. So you need to make the most out of every single photon. So I want them to know how astronomers do that, the tools and techniques they use. All right. This is the slide I have put up numerous times because the calculation of distance in astronomy is very important and very difficult. Remember, an object can appear bright in the sky because it's close to us, or it appears bright in the sky because it's intrinsically bright and it could be very far away. So looking at the brightness of objects does not tell us anything about the distances of those objects. If you remember, we need to know the intrinsic luminosity of the object to do that calculation. And then once you have the intrinsic luminosity, you measure the apparent brightness. And you guys can do that calculation now. Remember that wonderful equation with the log d in it that we used? That's how it's done. So when we're measuring the distances to galaxies or any object, what we want are standard candles. We want objects that we know their intrinsic luminosities, right? So they're called standard candles or standard bulbs. If you see an object in a distant galaxy, you measure its apparent brightness. If it's a standard candle, you know its intrinsic luminosity. You can do that calculation, and you have yourself a distance. So I'm going to talk about a few standard candles or standard bulbs that we use. One you've already heard of, we talked about these objects. Remember Cepheid variable stars? These are stars that pulsate. And they get very big and then they get very small. When they're very big, they're very bright. When they're small, they're not as bright. And they pulsate with a regular period. And the neat thing with Cepheid variables is that the period of pulsation is directly related to the luminosity. So the longer it takes for it to pulsate, the more intrinsically luminous it is. So this is great. We can use Cepheid variables to figure out how far away a galaxy is. So imagine yourself as an astronomer, and imagine you see a distant galaxy and all you want in your life is just to know how far away that galaxy is. As luck would have it, there's a Cepheid variable in that galaxy. What you do is you measure the period of pulsation. Let's say you measure the period of pulsation to be 10 days. So astronomers have already done the work for you. We have the plot of luminosity versus period for Cepheid variables. You just have to read off the graph what the luminosity is of your 10-day period Cepheid variable. You measure the apparent brightness, you do the calculation, and you have a distance to your galaxy. It's great, right? Very, very convenient. Yes, so far away, long period, greater luminosity, short period, less luminosity. Okay. This was one of the primary reasons Hubble was put up in Earth's orbit, was to measure Cepheid variables, and we'll see why in just a little bit. So Cepheid variables as a standard candle can give us distances up to 100 million light years, which sounds awesome, right? That's really far away. But there are galaxies billions of light years away. So Cepheids aren't the farthest standard candle. We need something that can get us beyond that 100 million light years. So what are we going to use? I will show you. Guys, remember white dwarf supernovae? Yeah. So if you recall, we talked about white dwarfs. This the remains of a star about the mass of our sun when it runs out of nuclear fuel. And sometimes a white dwarf is in a binary system, right? And then that binary star can accrete material onto the white dwarf. And then after a certain mass, the white dwarf tears itself apart. Just out of curiosity, does anybody remember what that number is, the Chandrasekhar limit or the white dwarf? Wow, yeah, you guys got it. Yeah, 1.4 solar masses, right? So if the white dwarf accretes 1.4 solar masses of material, it tears itself apart, right? And we have this white dwarf supernova. What's really great about white dwarf supernovae is that they are the same every time. The physics of a white dwarf supernova is the same, so its luminosity is the same. Every time one happens, thing reaches 1.4 solar masses, blows itself up, it's the same luminosity. If you see a white dwarf supernova, you know its luminosity. It is a standard candle. It's a standard candle. So here are just some photos of white dwarf supernovae, before and after pictures, and we use these to determine the distance to galaxies. These are great because they're very bright. So unlike the Cepheid Variables, which is getting us to millions of light years, white dwarf supernovae can give us billions of light years. So we can see white dwarf supernovae up to 10 billion light years. And seeing these white dwarf supernovae, we'll see next class how important these have been for our understanding of the evolution of our universe. The only caveat with white dwarf supernovae is that you have to catch one, right? They're just not there for you all the time happening. So if you are looking towards a distant galaxy and you want to know the distance, unless there's a white dwarf supernovae going off during your lifetime to see it, you don't know, right? So that's the only problem. So if white dwarf supernovae occur only once every few hundred years in a typical galaxy, you might not get lucky for the galaxy that you're interested in. Okay. But having these standard candles, the Cepheid Variables, the white dwarf supernovae, have changed our view of the universe. And again, next class I'll show you how fundamental knowing the distances to galaxies is to understanding how our universe has evolved and how it will evolve. But before we go there, we're going to go back in time a little bit, early 1900s and the state of astronomy in the early 1900s. We had some big telescopes, but at this point in time, we couldn't really see individual stars in distant galaxies. So you could see fuzzies through the telescope, but it wasn't clear if these fuzzies were nebulae in our own Milky Way or if they were something else. And there was a big controversy at the time, at the turn of the century. Is our Milky Way the entire universe, or is the Milky Way one of many, like, island universes in a much larger space? Now, today the answer seems obvious, right? You guys know there's billions of galaxies. Milky Way is one of hundreds of billions of galaxies in our universe. But at the time, this was a big debate. And in fact, they did an actual debate between two famous astronomers of the day. So on April 26, 1920, in Washington, D.C., two astronomers talked about this. Now, Harlow Shapley, I'm hoping the name's a little bit familiar to you. He's the globular cluster guy, right? You guys did what Shapley did in your last lab. You measured the positions of globular clusters and you found that the sun is not at the center. So that's Shapley. He's probably the more famous of the two. I doubt any of you have heard of Heber Curtis. But Shapley was the one who argued the Milky Way is the entire universe, which we now know is not true, right? And then Curtis had the counter argument that no, Milky Way is one of many, many galaxies or many island universes. And both of these guys had observational data to back up their claims for whether or not the Milky Way is the universe or not. And the debate ended up being a wash. At the end, neither gentleman came out as the clear winner. And so we had to wait until there was more evidence to prove, that Shapley was wrong and Curtis was right. That evidence came from Edwin Hubble and his collaborator, Milton Humason, who doesn't get a lot of credit, but he's an interesting guy. He dropped out of school in the 8th grade, but he's just like one of these naturally brilliant people. And he ended up working for the observatory that Hubble did his observations at, the Mount Wilson Observatory in California. And he was first like bringing equipment up and down the mountain. Then he worked as a janitor at the observatory, and then he was kind of a night assistant. And eventually he started working with Hubble, and he made such an impression that he was taken on as an astronomer at Mount Wilson and published with Hubble a very important paper on the nature of the universe. So I think I may have put up that picture of Hubble in a previous lecture. Hubble, again, he was an astronomer. This is early 1900s when Hubble is doing his work after World War I. And this is the telescope they were using, the 100-inch telescope on Mount Wilson, biggest telescope of the day. And if you go to the Air and Space Museum on the Mall, there's a little gallery. I've probably told you about it, the Exploring the Universe gallery. You can see part of this telescope. They have like a piece of the observing cage there that you can look at. And I think they actually have like a little mannequin of Hubble sitting there as well. Okay. So there he is. With this telescope, finally, Hubble could resolve individual stars in the Andromeda spiral. We're calling it the Andromeda spiral because we don't know that it's a galaxy quite yet. So he's looking at this galaxy. Of course, that's not the image he took. This is an actual Hubble Telescope image. But he can see stars in it. And if he can see stars in the Andromeda galaxy, he can see Cepheid variables. And if he can see Cepheid variable stars, he can get the distance, right? He can get the distance to this galaxy. And that's what he did. And I tell you this because I know there's a question on your homework about how did Hubble determine the distance to the Andromeda galaxy? He used Cepheid variable stars as standard candles to get this. And what he found is that the Andromeda galaxy is definitely not part of the Milky Way galaxy. It's beyond the Milky Way, all right? This is huge. Because now the answer to the debate question has been given to us, right? The Milky Way is not the entire universe. The Milky Way is one of many island universes or galaxies. This caused a paradigm shift. Just like we talked about going from the geocentric model to the heliocentric model, or going from thinking we're at the center of the galaxy to out towards the edge. This too, we're not like one galaxy in the universe. We are one of many galaxies in the universe. This is a paradigm shift, all right? And it all started from Hubble looking at the Andromeda spiral, or the Andromeda galaxy. So Hubble continued his work with Humason, and they measured distances to many more galaxies. And they took spectra of these galaxies, and what they found were that the galaxies were red-shifted. And I'm hoping you remember about the Doppler shift, that when something is shifted towards the red, it means it's moving away from us. So he found that most galaxies are red-shifted. And he also discovered this: the farther away the galaxy, the greater the redshift, meaning the farther away the galaxy, the faster it's moving away from us, which might be kind of weird. Like, why would that be the case? Like, why is that happening? So this is what a plot of velocity versus distance looks like for all these galaxies. So these dots are individual galaxies. So you can imagine, as an astronomer, you went to the telescope, you took spectra of these galaxies, you calculated their velocity, and you determined their distance, maybe using Cepheid variables. And what you find is a linear relationship between the velocity and the distance. Now, how many of you remember the equation of a line from your, I don't know what class that would be, the algebra equation of a line? Who remembers the equation of a line? Y equals plus b. Yes, y equals mx plus b. So what is my y in this plot? Velocity, exactly. And what does the m mean in this equation? That's the slope, right? So m is slope. We'll leave it as m right now. What is x in this one? Distance, very good. And who remembers what that b represents? Yeah, I'm hearing it. The y-intercept, right? And this y-intercept here is 0. So we can get rid of that guy, right? We don't need him because the y-intercept is 0. So this is a really, really important plot. So the slope for this plot gets its own special name. The slope we call the Hubble Constant, or H0, because it's special. We'll see why it's so special in just a second. So the equation of this line is the velocity, the recessional velocities of these galaxies are equal to the Hubble constant H0 times the distance. And this is a very important law. In fact, this is Hubble's law. This is Hubble's law. The velocity is equal to H0 times distance, all right? And H0 we'll see is an important constant. And H0 is the slope. I'm hoping you guys remember slope is rise over run. So change in velocity over change in distance. I'm telling you this because you're going to do this today during lab. You're going to make a Hubble plot, you're going to calculate the slope, and you're going to use that H0 to do something very interesting. Okay. I also want to mention the units because they're a little weird. So the slope is rise over run, which gives you kilometers per second for the velocity over millions of light years. So it's kind of a handful as far as units go. So the slope is kilometers per second per million light years. Sometimes it's in millions of parsecs as well, but that's the units of slope for this plot. So using this equation, we can calculate the distance to any galaxy, right? So we've done the work, right? We have this linear relationship. We've measured the redshift and distances of many galaxies. Let's say you have a galaxy that you don't have a Cepheid variable and you have no way of measuring its distance. You can very easily measure its velocity. All you got to do is take the spectrum, right? Take the spectrum, get the redshift. Using that, you can get the velocity, and then you can use your value for the known value for the Hubble constant, and you can get its distance. So it's a very convenient way to get at the distance of distant galaxies. There are a couple issues. First of all, not all galaxies obey this law perfectly. Galaxies are in clusters, kind of like a swarm of bees, right? So some are moving towards us while some are moving away. So it's not always perfect. And also the distances you calculate are only going to be as good as that Hubble constant, right? So that Hubble constant is only as good as the galaxy we've previously measured, right? So we want a really good value for that Hubble constant. That was one of the main reasons we put the Hubble Space Telescope, was to measure Cepheid variables and white dwarf supernovae and measure distances to galaxies. And the value we have right now is somewhere between 21 and 23 kilometers per second per million light year. And the different methods have validated this value. Okay. So, bring this all together back to what's happening. What did Hubble find? Hubble found most galaxies are moving away from us. Hubble found that the galaxies that are farthest away are moving away from us the fastest. What does this mean? Oh my goodness. It means, yeah, the universe is expanding. Space is expanding. And I don't want you to get confused. You guys are probably a lot smarter than I was when I was your age. So I'm just going to tell you what confused me when I was a young sprout and taking my first astronomy class. I heard about universal expansion, and in my mind I thought about a ruler. And I imagined like the ruler expanding, I imagined like the tables expanding and myself expanding and everything expanding. That's not what's happening, right? There is enough gravity within the Milky Way and everything that stuff like us, it's not expanding. What is expanding is the space between galaxies, just the space between galaxies. I should say just the space between galaxy clusters. So don't get confused, all right, like I got confused. It's the space between galaxies, not the stuff within the galaxy, all right? So you and I are not expanding. Coffee cups are not expanding. Chairs are not expanding. It's only the space between galaxies. Now, we'll learn next week that in many 100 to 100 years or so, that's not going to be the case. And eventually gravity won't be able to hold things together and everything's just going to fall apart. It's pretty depressing, but we'll talk about that next week. For now, though, it's just the space between galaxies that's expanding, all right? So there we have space expanding. And I want to just mention this guy, Lemaitre. He was around the same time as Hubble, and like Humason, he doesn't get a lot of credit for his work. He came up with this idea of the expansion of the universe a little bit before or about the same time that Hubble came up with it. So he had derived Hubble's law as well, but he really doesn't get, as we know, it's Hubble's law, it's not Lemaitre's law. But I just want to mention he was a Jesuit priest who did a lot of the work on this as well. Okay, so getting back to this age of the universe idea and expansion of the universe. Okay. So if the universe is expanding, right, it stands to reason that at some point in time, stuff was closer together, right? At the beginning of the universe, stuff was really close together, and ever since then, we've been expanding. If we can measure how fast the expansion is happening, then we can figure out how long the universe has been expanding, and how long the universe has been expanding is the age of the universe. So this is what's really awesome about Hubble's law and the Hubble constant. Okay. Now I want to be clear, the universe isn't expanding into anything as far as we know. It's hard to think about this because I know when I think about the universe expanding, this is what I think about. I think about like a balloon or some sort of like ball with stars in it and it's just blowing up. So the universe is expanding, but there's nothing that it's expanding into. The universe is all that there is. And then there's not the universe, which is nothing. So as far as we know, the universe doesn't have a center, and it doesn't have an edge either, and there's no privileged position. So we're in the Milky Way. We see everything expanding away from us. If we go to a galaxy 10 billion light years away from us, we would see the exact same thing. Everything's expanding away from us. There's no center. We're not at the center. Nobody is at the center, as far as we know. Okay. So age of the universe is 1 over the Hubble constant. So this is why it's important to know the Hubble constant. So if the value that we get for the Hubble constant is too large, we would have calculated a universe that's younger than it actually is, right? Because h naught is in the denominator. Similarly, if we calculate the age of the universe with a value that's small for the Hubble constant, the universe is older than we think it is. For a Hubble constant of about 22 kilometers per second per million light years, we get a universe that's about 13.6 billion years old, right? So we think the universe is a little bit older than that, maybe 13.9 billion years old. You might be wondering at this point, like, I'm no mathematician, but 1 over 22 is not 13.6 billion years, right? You're absolutely right, it's not. So where did I get this number from? How does this work? Again, I'm going back to the units, where we have kilometers per second over a million light years. To get the units to work out, you need to convert the kilometers to million light years or vice versa, so that you end up with an age of the universe that's just in seconds, which you can convert to years. You will do this today during lab. You're going to compute the Hubble constant. And the one you get, we're going to get it in kilometers per second per megaparsec, so it's going to be closer to 70 something. When you get it, you'll see that in a little bit. Okay, so now we get the importance of the Hubble constant. So thus far, we've been assuming the expansion of the universe is constant. The slope is constant. It has been constant over time. But what if that's not true? What if the universe was expanding faster in the past, like went and then it started slowing down? That would mean that we would have gotten to our size where we are right now faster, and the universe would be younger than we think it is. What about the other scenario? What if the expansion rate is speeding up? The expansion rate of the universe is speeding up, then the universe is going to be older than we think. And we do think the expansion rate of the universe is accelerating. And it's white dwarf supernova data that gives us evidence that the universe is expanding at a faster and faster rate.